Hello, everybody. Good afternoon. So today we are going to talk about requirements and cross-validation, prediction, missing values, a lot of stuff. But before that, how was the guest speaker? Did you like it?
Yeah.
Was it good?
Yeah.
Okay. So do you want more? Okay. So we can have one more guest speaker. I think we have time for that. And yeah. So about discussions, some people told me they have missed the discussion or something. So I have decided that we can have 11 discussions. You just need to participate in 10 of them. So essentially, we will have 11 discussions, so you will have 11 grades, and we drop the highest one. Right? We drop the lowest one. We drop the lowest one. So good. So don't worry about the discussions if you missed one. And about the homeworks, we decided that from now on, you will have 2 attempts per homework. Is that good? Okay. Great. So, and we use the lower grade. No, we use the highest one. Go ahead.
So for like past, let's say like we didn't get like, if we didn't go to grade that we like do homework, would that second attempt like go back for it and we'd be able to retry them to like get that grade higher up? Or
No. It only applies to the future homeworks. Yeah. Not the ones that are past due. So you already know the answers.
is that including today's?
I think so.
Yeah.
Yeah. So that's about it. And the last item is about the teams. So you are supposed to build your own teams, and I will help you to make your own teams. In the last semester, in the previous semester, actually, I assigned students to teams. And so some students complained that their teammates did not work, they didn't know their teammates, or they didn't choose their teammates, so things like that. So this semester, I'm letting you to choose your own teams, and each team should be 5 students, 5 members. So you should have 4 teammates. But don't worry if you don't have 5 members. I will assign you some other students. So I will assign some other students to your teams to make your teams whole. So try to make your own teams, but I will help you to complete your teams. And if you want, you can use TeammateMe to make your teams. Just you go to the website, you search for MISI 262, and you find your section. And one of the organizations is MISI 262 at 5 p.m. That is the section. So you just join that organization. That will be your section. And you make a sub-team. And the sub-team would be just a team. And then you can just add others or search for others and just find teammates.
Do you have to do that if you have a team?
No, you don't. Just if you don't have enough teammates, you can just use teammate. So, but you can just try it and see how it works. It's a tool that can help you in the future. And teammateme.com. Didn't you see the announcement that I made? So, have you seen the announcement that I made yesterday?
I see it now.
Oh. So, the other thing is that at the end, when you found your teammates, however you want, after you found your teammates, you should just put your teammates' names or your names and your teammates in the groups that are in Canvas. So there are some groups in Canvas, and you should just join those groups. So you self-assign yourself to the groups in Canvas. So just touch with your teammates and decide which number you want, and you just join that number. Okay. And that's about it. So on Wednesday, we will have the team meeting. So you will touch with your teammates. And if you don't have a team, or if you don't have enough team members, I will assign you to teams. Or I may combine teams just to for complete teams. Okay. Any question? Any suggestion? So I think last week I covered complete information, right? And we talked about complete information. Did we cover complete separation as well? I think we covered complete separation too. So who said yes? Okay, what is complete separation?
I don't have the exact definition in my notes, but I just remember we did the example where we had, it was.
Can someone tell me what's the
Yeah.
complete separation? Anybody? Okay, go ahead.
It's when you split your variables into a variable to success and failure, right?
Well, you can perfectly separate your values for the dependent variable into zeros and ones using one independent variable. Just one predictor is enough to perfectly predict the dependent variable, right? So like this picture. So if you know the value for X, you know the value for Y for second. You know when it is going to be 0 and when it is going to be 1. Okay. So yeah, so this example that we had didn't have any complete separation. Was this the example that you wanted to mention?
And that was it.
Okay. So what was that example?
I just know we had the, it was like if X is greater than 15, you predict 0, and if X was less than 15, I think it was the graph, and I just remember seeing like a split between the bottom left side.
Oh yeah, so it was 21 years
Yeah.
old. Yeah. Okay, go ahead.
Yeah, I had a question about that. How do you do about that slide? It was about the drinking age, right?
Yes, it was about drinking age. Something like this.
It is complete separation there, but when is there not be if it's like, so the bottom represents not drinking, right? 0.
Zero represents not allowing,
Not being allowed to drink.
not being allowed to drink.
So 0 to 20, or 0 to 20. So would the gap be like in between 20 and 21?
Oh, you mean the age gap?
Yeah.
So,
So won't there be no gap? Because like right when you're not.
Yeah,
allowed to
you are
drink,
right.
it
So,
turns to be-
yeah, if we had, so if we collected enough data, probably the data would look like something like this, up to 21, and then we have, and it would just, this would be like this. So a good diagram would be something like this.
So that would be complete separation.
Yeah, complete separation. Because you know for sure when it is more than 21, it is going to be 1. But if it is less than 21, it is going to be 0. You know for sure without any uncertainty. So, any other question? So, did we talk about large sample size? The requirement for sample size. Okay. So when we used OLS, which was for linear multiple regression. For linear models, we could use OLS. With OLS, we can estimate the coefficients very well with just few data points because it is just linear. But when we have nonlinearity, we cannot use OLS. We are using an optimization technique called maximum likelihood estimation. And we are going to use an optimization technique to estimate the maximum likelihood. And then what happens is that we are trying to find the maximum of something in the space. And we are dealing with curvatures and nonlinearities everywhere. So if we don't have enough data points, it is going to be very difficult to reach that maximum just in the space. It is going to be very difficult to reach that maximum. And we need data points. We need a lot of data points, especially close to the maximum, close to the optimal point. So that's why we need a large sample size, generate a larger sample size when we have a logistic regression rather than multiple linear regression. As a rule of thumb, we need more than 150 observations or data points to estimate the coefficients in a logistic regression. But of course, if we have more variables, if our model is more complex, we need more observations. Okay. So as conclusion, you should check for 3 assumptions for logistic regression and 3 requirements. If you are violating any requirement, if you are not meeting any requirement, you have 2 ways to go. One is collect more data. When you collect more data, it is less likely that you have complete separation because it is possible that you find the data point on this side or on this side. So you don't have certainty anymore. And it is more likely that you have complete information because you're collecting data and you collect data from different regions. And most likely you can cover more regions if you collect more data. And also, of course, the sample size becomes larger when you collect more data. So collecting more data always helps with requirements. However, if you cannot collect more data, you can simplify the model. Drop a variable, combine 2 variables, and then use a function of 2 independent variables as 1 variable, or just drop 1 or 2 independent variables based on the multicollinearities that you see, or based on the regions that you don't have the data for, you know. Or you can simplify it very, in the extreme case, we can simplify it to a condition. Just instead of using logistic regression, you can just use a condition. So that's just extreme simplification. So if you have a perfect separation or complete separation, of course, you have to simplify it to a condition. That's about it. So we are done with assumptions and requirements for logistic regression and for multiple linear regression. Any question? So now let's talk about missing values. The next topic is actually prediction and cross-validation, but since you will have a team project coming soon, I want to teach you how to deal with missing values. And this is actually a very quick topic. It takes like 10 minutes. So here we have the script for that. missing values.r. If you go to the modules, in the advanced topic, the first R file is the missing values. Missing values.r, you can download it and you can see what I'm seeing here. So to use this script first, let's change the working directory. Change the working directory to course data. And we did the all state dataset. This is actually the dataset that you will use for your team project, all state. Remember that. It has 97 observations, 97,000 observations, and 25 variables. Flights has 26 variables. So let's see the first 10 observations for the columns, for all the columns. You can see that we have these columns. Risk factor is one of the columns, and it has NA in it. Some of the observations do not have any value for risk factor. The NAs actually mean no value, not available. So we don't have any value for them. Can go here and go to color state, just check the data and see what we have. So in our studio, you can just see the data set in a spreadsheet like this. So these are the variables that we have. As you can see, for risk factor, we have NA here, NA, NA. We have many NAs. Also for duration previous and C previous, we have some NAs. It's NA, NA, and but not as often. Very, very sparsely. No. So now here's the question. What can we do with these NAs? What can we do when we don't have the values for some variables at some points? For example, let's deal with risk factor. It has a lot of NAs in it. First, I want to see what are the possible values for risk factor. 3, 4, NA, 2, 1. These are the possible values, right? So it seems to me that there is no 0 here. We can double check which all state risk factor equals 0. Let's see. Nothing. Integer of 0 means none. So we don't have any 0, right? In this column, we don't have any 0. So my guess is that NA means no risk. And we have 1, 2, 3, 4 for risk factor. And NA probably means that there is no risk. Therefore, we can just replace NAs with zeros. That would be probably a good solution. We replace the NAs with zeros. So let's see where the NAs are. We can find the positions of the NAs using this. IsNA is a function that returns true for NAs and false for values. So IsNA of one state, for example, and I run IsNA, I see false, false, false almost everywhere except here. You see, I see some trues here because these are NAs that we have in risk factor. So if I say which, it gives me the locations of those NAs or the positions of those NAs, indices of those NAs. We have about 1,000 NAs in risk factor. Actually, I can just say the sum to see actually how many we have in total. So dollar sign risk factor is NA. So let's run this first. These are the trues and falses. I want to count how many trues and falses I have. How many trues I have? For this sum, 34,000. So 34,000 of the values for the risk factor are true. That's 34,000 NAs. That's a lot because the total number of observations is 97,000. So it's like 1/3 of our data has NA for the risk factor. We cannot just remove or ignore those data. We have to deal with them somehow. So since we don't have 0 for the risk factor, what we can do is that we can just assign 0 to the places that we have NAs. So instead of NA, we have 0. I'm assigning 0 to wherever I have NA. If it is NA, like here, so I get the position of the NA and then I assign 0 to it. This is the command that I need. So it assigns 0 to the NAs. Just to test and make sure that it happened, I'm gonna just get the unique. The unique is 34021. There is no NA anymore. Instead of NA, it's 0. We have 0 instead of NA. Good. So we fixed the problem with the NA for risk factor. Now let's calculate the mean for duration previous, the average for duration previous. Oh, it returns NA. Why? Because apparently there is NA, at least one NA in this column. Let's see the possible values in this column. These are the possible values. I use unique of all states $ duration underline previous, and it returns all the possible values in this column, which are 2, 13, 4, 3, NA. We have an NA here, you see. So NA is one of the possible values. That means what? We have NA here. How can I calculate the mean if I have NA?
I have a question.
Sure.
So wait, so when you got mean for NA, is that just telling you there is one NA in it? Or it can't
At least one NA. Yeah, it cannot calculate the mean. When there is an NA in the column, there is an NA somewhere in the column, it cannot calculate the mean anymore. If we tried it with risk factor, also it would give us NA, but of course not anymore because we fixed it. We assigned 0 to NAs. So how can we deal with the NAs in this column? The NAs are not that common, but the problem is that we have 0 already here. We already have the value of 0 there. So we cannot just assign 0 to NAs. 0 means something which is different from NA. So what can we do? There are 2 different approaches. One approach is to remove the NAs from the model, from the data set. remove those NAs from the data set. That's one approach. The other approach is to calculate the mean or the average and then assign the average to the NAs. So wherever we don't know the value, we have NA, we just use the average in those places. That's another approach. But to use the average, we have to calculate the average. We cannot calculate the average if we have NA, right? How can we calculate the average? We should just use this parameter here. NA.rm equals 2. NA.rm equals 2 at the end would help us calculate the mean when we have NA. It actually tells R to ignore the NAs and calculate the mean without considering the NAs. Just skip the NAs. So the average would be 6.09. This is the average without the NAs. So what I can do now is that I can just put this average in those NAs, like what I did here. I see, you see what I did here was that I put 0 in the risk factor wherever there was an NA. So here, instead of 0, I just put mean. I just use the mean of duration previous, NA.rm equals true. Just put this value, or I can just put it in some variable, call it just mean of previous something. So, and then I put this variable, the value of this variable, in the holistic duration previous, wherever we have NA. So for practice, just do it. Just try to do it and see what happens. It's exactly like what we did here for this factor. Another approach is that we omit all the NAs from the model. But omit, I mean, we omit the rows, the observations. So if an observation has any NA in it, for any column, we remove that observation. So let's do that. Since other than the risk factor, for other columns, the NAs are scarce, we can afford to do that. We are not going to lose much data. So to this end, we use NA.omit of all state, or of the data set that we have, of the data frame. So NA.omit is a function that returns the data frame without the observations that have NA in them. It just removes the observations that have NA in them. So all state clean would be this, and dimensions for the all state clean would be 96,170. So we lost about 800 data points, 800 observations. Go ahead.
So where would you put mean of previous to then find the mean with the value for what NA?
So you mean to replace it?
Yeah.
To replace. So what you do is like what the command that we have here. I put all state. Let me show you. All state previous of is NA wherever all state previous duration previous. So that means wherever the duration previous is NA. Okay. I put the value of mean of previous. So if I do this, actually, first I should find the value, calculate the value, and then when I run this, it's going to assign that to. But of course, there is no NA anymore because we omitted all of them. You should do it before omitting the NAs, right? So this command or this parameter in a.rm equals true is a very useful parameter. Just remember it whenever you see an NA. If you want to get the mean, median, variance, standard deviation, sum, anything. If you have an NA in the column or in the list, it's going to give you an error. Not an error, it's going to just return an NA, unless you use this parameter. So this parameter will fix the problem for you and will calculate anything you want, even if it has an NA. So this is a very useful parameter that can be used in almost any function. Okay. So I'm going to give you another example also, just to make sure that you understand how to deal with the missing values. This is the flights data set. We have had an example with the flights data set, if you remember. What was the example that we had? Remember categorical variables? We have a categorical variable, airlines, 12 airlines. We converted that categorical variable into 11 binary variables. Remember? That was the flights data set. So how big is this data set? More than 500,000 data points, more than 500,000 observations. And it has a lot of NAs. I'm not gonna just show you, but you can see the number of NAs here, 62,000. Okay. You can see the number of NAs in arrival delay. So just one column, arrival delay. 11,000 delay NAs in arrival delay. Do we have 0 in arrival delay? No, there is no 0. So, oh, sorry. Do we have 0? I want to see how many zeros we have in arrival delay. So I just say sum of the number of zeros like this. It returns NA because when I have an NA, it's not gonna be able to calculate the sum unless I put this parameter at the end, na.rm equals true. When I put this parameter at the end, it's gonna just calculate the sum for me. And it is 11,000 zeros. So it has 11,000 zeros. That means we already have a lot of zeros, and NA is different from 0. We cannot just use 0 instead of NA. Okay. So now let's see how big would be the data set if we omit all the NAs. 574. So it was 586,000. It becomes 574,000. So, and about 10,000 observations, 11,000 observations. That's fine. I think we can afford to lose that much. It's not that many because we have a very large data set. So we can just omit those observations and store the new data set into the flights data set.
So what that number is decreasing by is the NA factor or the rows that have NA?
The rows that have NA. So you mean what we are omitting from the data set? Yeah. So NA.omit omits the rows that have at least one NA in them. Any row that has NA in it for any column would be removed. Some rows could have multiple NAs in them, like NA for 3 different columns. So, any other question?
So when you do the sum of the arrival drive on equal to 0, how come you're able to get like an actual answer the second time you run it? If like wasn't there no zeros originally? We didn't assign 0. Or like
No, we don't know there was no zero originally.
Oh, okay, I understand. You couldn't calculate because there was NA.
We couldn't calculate how many
Okay.
zeros we have,
Okay, and then the NA.RM just, it allows you to calculate.
calculate the number of zeros. Exactly. So that's about it. Now let's go to the next topic. Which is prediction and cross-validation. So after we estimate a model equation, what can we do with it? What's the use of a model equation? First of all, you can interpret the coefficients, understand the relationships between the independent variables and the dependent variable. We talked about interpreting the coefficients. You can understand how good the model can explain the variance or the variation in the dependent variable, for sure. What else? How else can we use the model? Can use the model? Yes, you can use the model to predict. You can use the model to make predictions. That's the main purpose, actually. That's the main purpose of building the model. So how can we make predictions? So when we run the regression model, the outcome of LM or GLM would be something, a data frame. We call it fit. We can call it anything, but let's say we call it fit. It stores all the information, all the results of the regression. So we used summary to see the most important ones, but of course we have a lot more there. So if you want, you can access the estimated coefficients using the coef list. So one of the elements in this data frame is coef. So fit $coef is a list of coefficients. So coef 0 doesn't exist because the indices start from 1 in R. Coef 1 is the intercept. Coef 2 is the coefficient for the first predictor. Coef 3 is the coefficient for the next predictor, etc., etc. So these are the estimated coefficients. And you can use the estimated coefficients to form the estimated equation model. And then you can use the estimated equation model to predict the values for the dependent variable. So for example, we estimated this equation model for the packages dataset, right? Remember? So we want to use it. We can answer this question. If the percentage of our sales package is 22% and the weather condition is 50%, what would be the average hours per driver? You just put the numbers, you just plug in the numbers in the equation, and or we just plug in the numbers in the equation like this. We don't need to put the numbers for the coefficients. We can just use these terms for the coefficients. $50 coef 1 plus $50 coef brackets 2, etc. And this way we can calculate the left-hand side, which would be equal to the right-hand side. And it is the average hours per driver. So we expect to see 12.26 hours on average per driver if we have 22% of oversized packages and weather is 50%. Right? What if the percentage of oversized packages is 3% and the weather is 100%? What then? That's easy. We just plug in the new numbers into the equation, and we find that it is 4.72 hours on average per drive. If it is 8% and 30%, we calculate and we find that it is 8.18 hours. So you see, for each case, we can just calculate the expected value for the dependent variable. What we calculate is the expected value. What we predict is the expected value, of course. Why would we do that? We want to make plans. We want to make better decisions, right? So knowing the future helps a lot. Knowing the future helps a lot. If we know how many hours a driver we need, that would help us to make better plans. Let's look at another example. The prices data set. In the prices data set, we try to predict the market volume using the Biggs Close, options expression, and FOMC. 3 predictors. We calculated, we estimated the coefficients, and we have this estimated equation model. Now, what would be the trading volume? What we expect to see as the trading volume for tomorrow if Biggs Close is 10, FOMC is 1, that means it is an interest rate release date, and options expression is 0. It is not an options expression. It's going to be like this. So we plug in the numbers and we find this value for the dependent variable. 6 billion shares, more than 6 billion shares, right? So we have more than 6 billion shares on average, or we expect to see more than 6 billion shares. That's what we expect to see. It can be higher or lower, of course, but that's what we expect to see based on the equation model that we estimated. If VIX is 25 and it is an options expression day, it's going to be the numbers, or we can just use the coefficients like this. And of course, the value for options X would be 1, and the value for FOMC would be 0, right? So the binary values, the binary variables can be used just like the continuous variables. And the result would be more than 10 billion shares. We expect to see more than 10 billion shares traded on such a day. Another example. So Biggs Close is 15 and it's just a regular day. So FOMC and options X are 0, both of them. We plug in the numbers and we find that the expected market volume would be 6.4 billion shares on such a day. Why would we want to do that? Making better decisions, making better plans, right? We want to make better decisions. Knowing the future helps us make better plans. So now let's talk about testing the model. We talked about prediction. We talked about how we can use the model. So just a naive approach to use the model would be like this. First, we build the model using all the data that we have. We have all the data from the past. We use all the data that we have up to today to build the model and estimate the coefficients. And then we start using it. And one day we predict the market volume to be 6 billion shares. At the end of the day, we see that the market volume is 6.5 million shares. billion shares. So not much difference. The next day, we predict the market volume to be 10 billion shares. At the end of the day, we see that it is 9 billion shares. That's fine. So we have a good model. The next day, we predict the market volume would be 7 billion shares. But then we see 13 billion shares. Oh, now we have a problem. Large difference. We didn't expect that. So our system crashes. We have several problems. So it's not a good idea to use this model. And we found out too late. This is not a good model, and we found out too late. We should have tested the model somehow before using it. So we just assume that the model is going to work well, but what if it doesn't? So what can we do? We can cross-validate. Cross-validate is what we use when we have a large enough data set and we want to make sure that the model that we built is accurate and valid. So this is usually used in machine learning. So now we are entering the territory of machine learning, actually. So in cross-validation, what we do is that first we divide the data into training and test set, a training and a test set. We use part of the data for training and part of the data for test. Usually 70% of the data is used for training and 30% of the data is used for testing. Then we build the model, estimate the coefficients only using the training set. So we use a training set to train the model or estimate the coefficients. So when you hear the term training a model, that simply means calculating the coefficients, estimating the coefficients, or running regression. That's it. That's training. So then we use the estimated model, the trained model, to predict the dependent variable in the test model, in the test data set. So we use the training data set to estimate the coefficients. Now we use the coefficients on the test data set to predict the dependent variable in the test data set. Then we are gonna just compare the errors in the training data set and the test data set. If the average errors are similar, that means the model is stable and we can use the model for the future. If the errors are not similar, that means if, for example, the errors on the test set are much larger, that means the model is good in predicting the past, but is not good in predicting the future, which is the whole purpose of the model. So let's go and see that visually. So in cross-validation, what we do is that first, let's assume that we have a time series data set. Okay, let's assume we have time series. We go to the past. We move back in the past. Let's say we go back 2 weeks. We build the model based on the data that we have before that point. All the data that we have before 2 weeks ago. Okay. We estimate the coefficients. We call that data the training set.
Then we apply the data on these 2 weeks, which is actually the future for the model. The model has not seen those data. We use the estimated model on the test data set, which is actually the data that we have for these 2 weeks. After that point, that hypothetical present, and see how the model can predict its future. And then we decide if the model is good or not. If the model is good, then we can use it in actual future, in our future. So the test data set is actually the model's future, but not our future, right? Because we already know the values for the dependent variable. We already know all the data. The model doesn't.
Wait, so how do you know when the model is good?
So I'm gonna explain in detail, but when the error for the test, error on the test data set is around the same level as the error for the training data set. That's when we know that the model is stable, at least. But what we care about the most is the error in the test set. So visually, what we do is this. We split the data into a training set and a test set. 2 subsets. We use the training set to estimate the coefficients and run the regression, right? Run the model. And of course, we can get the residuals and the distribution of errors as a result. So, you know, the output of the LM function includes the residuals. Okay. And then we use the same model, the same coefficients that we estimated, to predict the values in the test set. And we try to predict the values in the test set. However, we already know the actual values in the test set, right? We already have the actual values. So we can compare the predicted values to the actual values and see how good our model is. And we can calculate the errors, the distribution of errors, the actual errors, and see how good our model is. Let's go through an example. The packages data set. So in the packages data set, we have a time series. We have days. So we are dealing with a time series, right? So what we do is that first we divide the data into training and test sets. So the 70% of the data should be in training set and 30% of the data should be in the test set. Okay. If we are dealing with a time series, like packages data set or like prices data set, we use the first 70%, the earlier 70% for training, and the rest for testing. Like what I showed you, it's like we are going back in the past. You know, we're going back in the past, and we are just estimating the model from some point in the past. However, if our data set is not a time series, it is not chronological, there is no order between the observations, what can we do then? In that case, we're going to take a random sample of the data. We're going to select a random sample and use it for training. 70% of the data randomly selected, used for training, and the rest of it used for testing. We use 70% of the data randomly selected for training, and then we use the rest of the data set for testing. So many of the data sets that we have are actually not time series, like the nonprofit data set, employees, taxi, flights, you know. So that's about it. In this case, in this particular case, packages data set, we are dealing with a time series data set, and we just should take the first 70% for training. How can we get this first 70% for the earliest 70%? It's super easy. 0.7 times n would be the number of observations that we want to use for training, right? Right? Okay. So from index 1 to that point, whatever it is, to that number would be the positions of the observations that we want to use for training, and the rest is used for testing. On the other, if it was not a time series, if we were not dealing with a time series, we would randomly select 70% of the data for training. And this is how we use, this is the command that we use for random selection. Sample of 1 to n. So the population would be 1 to n, like 1,000 data points. And then how many data points do we want to select randomly? 70% of it. So 0.7 times n, 700, for example. And at the end, we should also put this parameter replace equals false, because we just want to select 70% of the data randomly without replacement. We don't want to select any observation twice. Okay, we just don't replace back any observation that we select randomly. So we just use this function, sample of 1 to n, comma, 70% of n, comma, replace equals false, and it will return a list that has a length of 0.7 times n. And that would be the positions or indices of the observations in the training set, for the training set. And of course, the rest will be used for testing. So yeah, so far so good. We can switch to R. So I show you how to do it on R. If you like it, you want to go to R. So let's the script that we are using is this linear regression prediction. It is in the next module, prediction module. So let's go to the prices data set. Actually, let's go to the packages data set. The example that we have. Packages data set. I'm gonna change the working directory. Read packages.csv. Of course, these are the columns that we have as a reminder. How many observations do we have? 730 days. 730 days. Okay. What portion of the observations should we use for training? 511 days. 0.7 times n. That would be 511 days, right? So the training data set would be, the indices for the training data set would be from 1 to 511. 0.7 times n would be 511. So the training data set, the positions for the observations in the training data set would be from 1 to 111. And the test would be the rest. Remember that the test data set would be the rest of the data set. So how can we find the rest? This function set diff. Set, like a data set difference. So difference between what and what? 1 to n, the whole data set. 1 to 730. Day 1 to day 730. 1 to n. Minus train. Minus train. So the first parameter minus the second parameter. So train is 1 to 511. So set diff would return 512 to 730. From 512 to 730. That would be the rest of it. So if you don't believe me, you can just see train is like this. 1 to 511. And test would be like this. (512) to 730. And the length of test would be 219. 219 data points are left for testing. Okay. So it may not be precisely 30% and 70%, but that doesn't matter. It can be just around 70% and 30%. So how can we create the data sets? We have the indices, we have the positions of those data points. We should just use d of those data points and put that in the training set. D of train, it would give us the training set. D of test would give us the test set, right? So far, so good. Now, let's say we want to estimate this equation. Average hours per driver as a function of percentage of hour size and weather conditions. Two predictors to predict the average hours per driver. So we use which data set? You have the training data set, the test data set, and the whole data set. Which one do we use? Which one do we use? Training data set. The training data set. So LM of the train, $sign average hours per driver as a function of the train, $sign percentage of hour size plus the train, $sign weather conditions. And it would give us, it would estimate the coefficients for the model using only the training set. Okay? Using only the training set. So now I want to just teach you something that makes it a little bit easier to use the LM function. So instead of just putting this data set $sign each variable or each column, you can just use the column names and at the end put data equals the train, the name of the data set, the name of the data frame. Data equals the name of the data frame. You just put it at the end, and this is going to be just a little bit shorter. So it's equivalent to the other one, almost equivalent. Okay. So summary fit would give us the estimated coefficients using the training set. Using the training set, these are the estimated coefficients. 3 coefficients, all 3 are significant. Good. And of course, as we discussed before, we can access the residuals, in the model using the receipt list. Fit $sign receipt will give us the residuals. How many residuals do we have in this model? Can anyone tell me? How many residuals should we have? If anybody answers, they get 100% bonus points. All the bonus points if you answer this question. Go ahead.
Well, of the things that you're testing, is it 3?
3?
Yeah.
The number of residuals? No. 5? No. No, no, no. So the number of residuals are the number of errors. That the number of data points, right? How many data points do we have in this model? 511. Because we used 511 data points for training. That is the size of our training set, right? So the number of residuals would be 511. You can see that here. Length of fit $sign receipt 511. So that's about it. Now let's see how we can so the residuals are useful to estimate. So these are the residuals. You can see the residuals here using the histogram, hist function. You see this hist function. Just you see the residuals have a normal distribution. So that's good. That's good news. They have normal distribution as we expect. It's one of the assumptions. And they can be negative or positive. So we want to have a sense of goodness of the model. You know? So the absolute value for the residuals would be what we are interested in. And the mean of the absolute values would be some indication of how some indication of the mean of the absolute values. I don't know why it didn't run first time, but it's 0.6, the average of the absolute errors. Okay, if I say the average of errors, it would cancel out negative and positive errors. Go ahead.
I'm confused. So the training set that's considered the errors?
No. Now I want to see the average error for the training set. That's the first thing that I'm trying to see. So if I get the average errors, the negatives and positives cancel out each other. So I'm calculating the average of absolute values for the errors. And it is 0.6. And I can compare it to the value to the average for the dependent variable. See how big it is. The average for the dependent variable is 6.47. So I think it is like, let's say, it's like this, like about 10%, 9%. It is 9% of the value for the dependent variable. So the value for the dependent variable, whatever it is, the average error would be 9% of that. That's the size of the error that we have in training data sets. Okay, in the training data set. Now we get to the interesting part. I want to calculate this for the test data set too. So I compare. How can I calculate the error for the test data set? I didn't use the test data set to estimate the coefficients, right? Here, what I do is that I use the estimated coefficients that were based on the training data set on the data that I have in the test data set to calculate the dependent variable, to estimate the dependent variable, to predict the dependent variable in the test data set. So this is the formula. It is prediction. Just our old prediction formula with $sign coefficient, etc., times the value of the independent variable, and then etc. So we have the formula, the estimated formula, except in this formula, the coefficients are derived from which data set? The coefficients are from the training set. The X values, the predictors are from which data set? The predictors, the values of the predictors are from the test data set. So essentially, we are outside the test data set. We have calculated, we have estimated some coefficients, and we want to apply those coefficients in this new data set, the test data set, and see how good it can predict this new data set, right? How good this model can predict the dependent variable in the test data set, which is new to the model, So we calculate the dependent variable for all the points, all the data points in the test data set. 219 data points, right? So like this, so we have the list, and it should be 219 data points. So we are running out of time, but this is another way that we can predict. We can use prediction. When we have the coefficients fit, we can just apply the coefficients on the values on the predictors like this, using the predict function. So we're going to continue on Wednesday. Thank you.